All right, welcome. In this video, I'm going to be telling you about properties of logarithms. And so to start, I think you should practice your logarithms. Just, make sure you understand what we talked about in the last unit. So I'd like for you to try these 9 logs on your own, see if you know what you're doing, check your work against mine, because this can pop up in like 5 seconds. All right, there you go. Now, if you've got most of these right, you're good to go. Especially the kind of the top 3, maybe the first 5 or so. Like if you're good with the basic ones, let's go. Let's talk about the log properties. If you don't understand how to get these, you probably need to go back and continue practicing logs. Watch the video again. Let me give you the lesson again. Get those straight, because that's what's really important as far as takeaways from Algebra 2, in my opinion. Much more so than the properties of these logs. Okay, at the end, we'll come back and we'll fill out this here chart that's going to give us all of our log properties, so it's something that you could refer to in the future. But now, let's get on to our first property. All right, so our first log property has to do with really products. So we've talked about this repeatedly in Algebra 2. If we have b to the x times b to the y, that's where we add the exponents. That's b to the x plus y. That has come up so many times I can't even really think of all the different places that we've talked about it. Okay, so the equivalent log rule, and I'm just going to kind of help you discover this, would be if we went to take the log with base 2 of 2 to the 4 times 2 to the 3. Okay. Now, on one hand, we could combine these and use that exponent property and say, okay, that's going to be log base 2 of 2 to the 7, and that's going to be equal to 7. But I'm going to show you that this is equal to the log base 2 of 2 to the 4. I need to move this down, yeah. Plus the log with base 2 of 2 to the 3. Because really the log is the exponent, right? The exponent I put on 2 to get this is the sum of the 2 exponents, x plus y here. Okay, so that's what we're saying. Okay, this is log base 2 of 7 equals 4 plus 3, 7 equals 7. Okay, so let me copy in the rule. Is that we can take the log of a product by evaluating the log of each of the factors and adding them together. So it goes from product to sum. Okay, and let's do a couple of examples. I think that would be good for us here. All right, so the first one is if log base 2 of 7 plus log base 2 of 5 is equal to log base 2 of x, then what's x? Okay, so what we're going to have to do is combine these into a single log. Okay, so this is kind of applying the property in reverse. So we saw that the log of a product is equal to the sum of 2 logs. So, well, if I have the sum of 2 logs with the same base, I can combine their arguments into a product and say these are going to go down to log base 2 of 7 times 5. Okay, so that means that x is going to equal 35. Find the value of log with base 9 of 27. Okay, so that was one that was on the front page, and maybe that one was one that you didn't get right, and I was saying okay, if you don't get that one, don't worry about it. I just want you to be able to do the basics. And so what we do here, before I'd have said, all right, 9 to the what equals 27, and then kind of solved an exponential equation, but maybe I can rewrite 27 as a product of 2 things that I know the log with base 9 of. So I'm going to call that 3 times 9 is 27. So this is going to be log base 9 of 3 times 9, which will equal log base 9 of 3 plus log base 9 of 9. Each of these things, I think, are a little easier to digest than just log base 9 of 27, especially if you're new to this stuff. Okay, so what exponent do I put on 9 to get 3? I would put the half exponent on 9 to get 3, because 3 is the square root. And then what exponent do I put on 9 to get 9? That's 1. So that's 1 half plus 1. That's 3 halves, like I said at the beginning of the video. Okay. Now we're going to use this table of approximated log values to approximate the value of log base 3 of 330. Okay, so what we need to do is we need to be able to make 330 out of 10 and 11. And I guess 3. Okay, so what we're going to need to do is, 10 times 11 is 110. I would need to multiply that by 3 to get 330. So I need one extra value that I have to know on my own, right? It's not a decimal. Okay, what exponent I put on 3 to get 3? That's 1. Okay, so I'm going to put that there. I'm going to say 330 can be written as 11 times 10 times 3. Okay? And so I can go from those products to a sum. So it's a log base 3 of 11 plus log base 3 of 10 plus log base 3 of 3. You can see that. Okay, so I'm going to look each of these values up from the table, and that'll be 11 was 2.2, 10 was 2.1, plus 1, so I've got 2.2, 4.3, 5.3. I like these problems a lot. These ones where they give you an approximate value and you have to approximate a different log using properties. I'm a big fan of this problem type. So you can expect to see that on the homework. You can expect to see that on the quiz next time. And you can probably expect to see that problem type on the on the test eventually at the end of the unit. Okay, over here, okay, actually finding the value of these. Okay, both of these are bad numbers, like if you were to evaluate them with a calculator, but they combine to make a nice number. Okay, so what I'm going to do is I'm going to combine them first, okay, kind of like I did at the beginning. Combine them into product. So 3 times 12 is 36. And what exponent do I put on 6 to get 36? I get the 2 exponent. Okay. And then, okay, these last two, I remember this one was a little tricky. If log base x of 9 equals 13, what's the value of log base x of 9x squared? Well, you might be like, yeah, we don't know how to do that yet, but we do. We're going to look at that as the product of 9 times x squared. Okay, so that would be log base x of 9 plus log base x of x squared. Okay, so log base x of 9, that's 13, plus, okay, and I think to myself, what exponent do I put on x to get x squared? That's the 2 exponent. So that's 13 plus 2, and this will be equal to 15. Okay. And if log base x of 9 is equal to 13, what's the value of x? This is a little bit this is a little old for us. Like, this is kind of going back to the last lesson, I think. But we're going to rewrite this as an exponential relationship and then try to see what shakes out from there. So the base of the log is the base of the exponent. Okay, so x to the log is the exponent. So log is equal to 13. That means the exponent's 13. That's equal to 9. But we just want the value of x. So I might take the 13th root of both sides and say x is equal to the 13th root of 9. Okay, and that's just a number. Nothing to be scared of. Okay, so now I think, yep, that's all. Let's talk about our next log property. All right, so the next one is going to go back to the idea of dividing two numbers that have the same base and different exponents. And in that case, we have seen in this class, we subtract the exponents. Okay. I'm saying, okay, and I need to go to like a log base 2 example. So I'm going to say, I didn't really have one thought up already, but I think I'll do 2 to the 7 divided by 2 to the 4. I don't like that. Okay, so what I mean, you might see this coming, but I'm going to write this, instead of 2 logs, I'm going to write it as a difference of 2 logs, right? Because we've got that difference here. So what I'd be doing, what exponent do I put on 2 to get this? Well, it would be the 7 minus 4 exponent. That's what we're getting at. So over here, that's going to be log base 2 of 2 to the 7 minus log base 2 of 2 to the 4. So on one hand, I could say, okay, this is log base 2 of 2 to the 3, and then I'm getting 7 minus 4, and that's also 3. That's some evidence. So in general, let me tell you the rule. That's when we're taking the log of a quotient, we can take the logs of each of the things we're dividing separately and subtract them. And this is kind of like the product, a somewhat useful property. And so I think we should work some examples. All right, so I like this. The first one's starting us off pretty easy, kind of like the other one. So we're going to use our product and our quotient rule here, right? Because I've got a sum and a difference. So maybe I'll do these two first. And I'll say log base 3 of 4x minus log base 3 of 5 is equal to log base 3 of 6. And then I could combine. Now, I think in the long run, you're just going to be like, okay, plus and minus, I'm going to multiply the 4 by x and then divide by 5. But, maybe you aren't seeing it, and so I'll just go step by step here. Okay, so log base 3 of 4x divided by 5. And that's going to equal log base 3 of 6. Okay. Now, we haven't talked a whole lot about solving equations, but I think it is self-evident that if these two logs are equal, it's because the things on the inside are equal. So 4x divided by 5 needs to equal 6. So what I'm going to do, I'm going to start by multiplying both sides by 5. So I get 4x equals 30. And then divide both sides by 4, and I would get x was 30 divided by 4, which I could reduce if I needed to 15 over 2, or 7.5, however you like it. And that's us finding x. All right, find the value of log base 2 of 80 minus log base 2 of 5. This is another one where once I simplify it, it'll be something I'm able to take. 80 divided by 5. Okay, remember that division by 5 is a lot like multiplication by 2. So this is going to be 16, right? Because 8 times 2 is 16, or it's half of 80. No, it's a tenth of 2 times 80, or whatever. However you want to look at it. Log base 2 of 16. Ask yourself, what exponent do you put on 2 to get 16? You put 4 exponent on 2 to get 16, so that's going to be 4. Now we're going to, estimate a log value using a table of values. And so 0.88, I think that's going to be, that's 88 divided by 100. So 8 times 11 divided by 100. Okay, so 8 times 11 divided by 100. All right. And, I definitely like this one because this is kind of leaning towards the next log property. It's like, I've only got log 10, but this is 100, and it's 10 squared. You'll stop. Come back. I think about this one when we go and talk about power of power. So I'm going to say that this is equal to log base 3 of 8 plus log base 3 of 11, because those are both in the numerator, minus log base 3 of 100, which I might at this point call 10 times 10. Okay. And then, and I think maybe I will also just put like a square bracket around this. Maybe you see why I would do that. If you do, then you can see what's coming here. Log base 3 of 8 is 1.9. Plus log base 3 of 11 was 2.2. Okay. Then we're going to subtract. Well, this thing here would become a sum of 2 logs because of that multiplication. So I'm going to need to subtract the log with base 3 of 10 twice. Since I've got 2 powers of 10, I end up with twice the log. That's going to be the next property. But in here, I'm going to just say, all right, log base 3 of 10 plus another log base 3 of 10, which we could look at as 2 times the log base 3 of 10. And so that's getting at the property here. Okay, that was 2.1. So I'm going to have 4.2. 4.1 minus 4.2, is that right? It's negative 0.1. Hard time believing that. Yep, sure enough, I grabbed a calculator, I checked it. It's true. It's about negative 0.1. Just, trust the properties. Okay, they're not going to lead you wrong. Okay, write this thing as a single logarithm, natural log of x minus 6 minus natural log of x. Okay, so we could just divide the arguments, and I'm going to say, okay, that's natural log of x minus 6 divided by x. That's a single logarithm. We're good there. Rewrite this in terms of log x and log y. I like this problem a lot. Rather than saying write it in expanded form, or we have to define expanded form and then say what we mean by that, I can just ask you to write this in terms of the base 10 log of x and the base 10 log of y. So what we've got here is I'm going to split this out, and I'm going to write in I always like to write in the tens. Split out over the 100 times the x divided by y. Okay, so the times will become a plus. Log base 10 of x divided by becomes the minus. Log base 10 of y. All right, this is great. And except this is not only in terms of log x and log y that I need to deal with this. Okay, so what exponent do I put on 10 to get 100? That's the 2 exponent. So I'm going to say 2 plus log of x plus log of y to give it to them exactly like they requested in terms of log x and log y, common log, no base given, base 10 implied. Now, let's move on. So, kind of we're just traversing back through our exponent properties and then turning them into log properties. I don't think that the change of base formula is an exponent property, but if you notice that it is and there's something I'm not seeing, I'd ask you to bring that to me and let me know, because I'd love to be able to pitch it in terms of a relevant exponent rule. Anyway, I think when we take b to the x to the y power, we've done this a lot, this is where we're multiplying the exponents. So b to the x times y. Okay? So what I do kind of down here, let's say, I'm going to think about this. All right, so I don't know. I didn't really think of a very good one, or one that was as poignant as the other two. But I'm going to start with log base 2 of 8, right? And I can write 8 as a power of 2, which you might feel like is kind of going back to our fundamental identities, but what I'm saying is that the exponent we put on 2 to the 3 is 3 times as much exponent as what we would put to get log base 2 of 2. So I'm just proposing, I'm going to show you the rule, that this is equal to 3 times the log base 2 of 2. But on one hand, like, I already know that's going to come back 3 because of the definition of a log. And then this is going to be 3 times 1. We've taken this log base 2 of 2 enough times. We know this is going to be 3 times 1. That's what I've got for you, that this exponent can swing around the front with multiplication. So let's write that down as a formal rule. Right, so to formalize this, the log with any base of any argument to a power is going to be the power multiplied by the log of that argument with the same base. Okay, so I think maybe we'll just jump in and do some examples here. So what do we got? We have... rewrite this natural log in terms of natural log x and natural log y. Okay, gladly. Okay, looks like I've got a product and a quotient, so I'm going to need to split these out over their additions and subtractions first. So that would be natural log of e to the 3 plus natural log of x to the 4 minus natural log of the 5th root of y. But since this property is all about taking exponents and swinging them around the front, I probably need to write the 5th root of y as a power of y. So I'm going to write that as y to the 1/5. And then I'm going to, even though you could just say, okay, natural log of e to the 3, what exponent do I put on e to get e to the 3? It's going to be 3. I'm going to use the property. So I'm going to use that power property that I just told you about, plus 4 natural log x minus 1/5 of the natural log y. And right, we already knew this was coming back 3, but now it's 3 times 1. So it's still 3. Okay, so this is going to be 4 natural log x minus 1/5 natural log y. Okay. I am pretty sure that I've done a pretty good job on this video of saying natural log, but in general, when I say log outside of Algebra 2, I really only mean natural log. So, okay, if I'm writing 2 times base 10 log of x minus 1 minus 1/2 of log of x as a single logarithm, okay, well, then we're going to say, all right, I should probably write, use those exponents so I can write just one. Okay, so I'm going to have this equal to log base 10 of x minus 1 squared minus log base 10 of x to the 1/2. And then I'm going to kind of combine those two logs into one with the log of a quotient property. So I'm going to say that that's log base 10 of x minus 1 squared over the square root of x. And that's going to be as far as I can take that. All right, now we're going to do a couple of more approximations. So log base 3 of 10, 11, and 8 are given to us. The square root of 11, oh, that'll be not so bad. 11 to the 1/2. That's going to be half of the log with base 3 of 11. And it's going to be half of 2.2. That's going to be 1.1. Okay. And then log base 3 of 1 over 1,210. Okay, we didn't get this far in any of my classes, but I'm going to call this 1210 to the negative first power. Right? We're focusing on power right now. So I'm going to say that that's the negative of the log base 3 of 1,210. And then I'm going to have to write 1,210 out of these numbers. Well, 11 squared is 121. And then multiply by another 10, I'd get 1,210. So what I'm going to do, I'm going to hold on to this negative on the outside, and then I'm going to do the addition. All right, so I'm going to have 2 times the log base 3 of 11 plus 1 of the log base 3 of 10. So I'll have the negative of 2 times log of 11 would be 4.4, plus log base 3 of 10 was about 2.1. So I've got 6.5, that's negative 6.5. Okay. That was pretty involved, but if you think about it, we built up to this over the course of these 20 minutes we've spent together, learning our log properties. That we didn't just go straight for that. We learned all the other properties first. All right, now we're going to find the value of x. So this is natural log of 2 to the 4, which is 16, minus the natural log of 4 cubed is 64, is equal to the negative of log x. I think I'm going to just deal with this negativity later. Now you could multiply both sides by -1 and make this one positive and that one negative. I don't think that's necessary. Okay, I'm going to say that this is natural log of 16 divided by 64 is the same as 1/4. And maybe I'll deal with this exponent now. Okay. And again, we haven't talked about solving these log equations, but I do think it's self-evident that this means that 1/4 is x to the -1. Remember that x to the -1, that's just the same as 1 over x. So I'm going to say 1/4 equals 1 over x. And then we can solve this one with our eyes, and we're going to say x equals 4. All right, happy. Let's move on. Let's do the last property, the change of base property. All right, now the change of base formula, this is true for any base, right? So if I've got some sort of log with some base and some argument, I can rewrite that as the ratio of 2 natural logs. I can rewrite that as the ratio of 2 base 10 logs. I can rewrite that as the ratio of 2 logs with any base I like, provided it's the same base on top and bottom. And I'm going to prove this for you, okay? Because I think that this is a proof that we can understand. So, but I'm going to go fast. So suppose, I'm trying to see what letters I used. I probably am using letters in a confusing place, but u to the x equals a. Okay. What we know already from the definition of a logarithm is that this is equivalent to saying the log with base u and argument a is equal to x. But then I'm going to take the log with base b of both sides, right? I'm not committing to what b is, it's just some suitable base for a log. So I'm going to take the log with base b of both sides. Okay, and then I'm going to use that exponent property that I just showed you about, where I can swing that x around the front. So I'm going to say x times the log with base b and argument u is equal to log with base b and argument a. And then I'm going to solve for x by dividing both sides by log with base b of u. So x equals log with base b of a divided log with base b of u, which is showing us that, that this log with base u and argument a is the ratio of these 2 logs, just like it was up there. So this is why the change of base formula is true. Now let's work some examples. Let's see how we're going to put this into action. So change of base formula. All right. Yeah, the commentary here is good. Extremely useful if you've got a calculator that can only do base e and base 10, which college algebra CLEP only allows a scientific calculator. There are situations where this used to be a really big deal. We don't really use the calculator much in my Algebra 2 class, so we're not going to need to worry about that. But I can ask you interesting questions. Okay, this I would not classify as an interesting question, but we can write log base 2 of 5 as the ratio of 2 natural logs. Okay, remember that log base b of a is natural log of a divided by natural log of b. It's particularly easy to remember because in the original statement of the log, the a sits above the b. And then when I do the ratio, the a sits above the b. So over here, this is going to be natural log 5 divided by natural log 2. And, over here, behind the camera, when I'm checking things with a calculator, I use a TI-83, and it doesn't have the log base command, so that's what I do. That's how I evaluate logs. Works for me. I hope it works for you as well, if you have a TI-83. Right? So log base 9 of e to the 8 is equal to both a over natural log of 5. I'm just going to have to believe that. And log base 3 of e divided by b, what's the value of a plus b? Let me think about this for a second. How do I want to approach this? All right, so after some consideration here, I'm going to change that to natural log 5. I'm not saying that the original version of this question that I stole from a textbook or wherever I got it from wasn't natural log. Oh, I erased 5 and replaced it with 5. This would need to be a natural log 9, in my opinion, at least at the Algebra 2 level for us to work this out. So what I'm going to do is I'm going to set up two equations and try to work to solve them. So I've got log base 9 of e to the 8. If I'm going to try to write it as something divided by natural, I'm going to use the change of base formula and change it to natural logs. So this would be natural log of e to the 8 divided by natural log of 9. Okay, so that means that a is natural log of e to the 8, which is the exponent I put on e to get e to the 8, which is going to be 8. Okay, so all right. Then for b, I'm just going to set up another equation. Log base 9 of e to the 8 is going to equal, and in terms of log base 3, I'm going to have to get a ratio of 2 logs with base 3. So log base 3 of e to the 8 divided by log base 3 of 9. And it's like, okay, these are all fitting together. I can see exactly what I'm supposed to do here, but over here with the 5, unless there was something I'm missing, and if you see something that I'm not seeing, please bring it to me. Let me know about it. Say it in the comments or something. I just didn't think that was going to be. Not that it was impossible to solve. We could have, but at what cost? It would have taken a long time. Anyway, I'm wasting a lot of time talking about it. Let's say, all right, but this is just talking about log base 3 of e, so I need to get rid of that e to the 8. I'm going to bring that around as using that exponent property. 8 times the log base 3 of e divided by log base 3 of 9 is the exponent I put on 3 to get 9. That's 2. All right, so I don't have that 8 here. So I need to throw that 8 down here. And so if I had, an 8 in the numerator, that's like a 1/8 in the denominator. Okay. So that means that b is equal to 2 divided by 8, or 1/4. So a plus b is 8 1/4. I might just say, whoops, pardon me. That's 8.25. That's going to be good enough for us. All right, is there anything else here? No, that's it. So let's fill out our log properties table. Okay, the fundamental identities are that the log with base b of some power of b is very easy to take. It's just that power, right? Okay, because it's saying what exponent do I put on b to get b to the put the exponent on there. We also have the kind of the opposite property where if I take b to the log base b of x, that's going to be x as well, and that's not always as easy to understand why it's true, but I would just propose, okay, the log base b of x is the special exponent I put on b to get x. So if I put that special exponent on b, I should get x. Okay? And if you want to rewind that and try to convince yourself of it, that's fine. If you want to just come and have me try to explain it to you, I can do that too. All right, log of a product, the log with base b of x times y turns into a sum of 2 logs. Log base b of x plus log base b of y. Log of a quotient. If I have log with base b and argument x divided by y, that division turns into a difference of 2 logs. So that turns into log base b of x minus log base b of y. And now that you know all the properties, I propose that you can also look at this as a product of x times y to the negative 1 with that power situation. Anyway, log base b of x to some power. What I can do is I can swing that power around the front, and I can write that as p times the log base b of x. And then the change of base formula is the log with base b and argument a is equal to the log with base c of a divided by log with base c of b, where c is any base I like it to be. Okay? So those are our log properties. I explained why they were true. I did some examples of all of them. At this point, I think you just need to practice on your own. So that's going to be all for this video. Thanks for watching. Hope it helped.